Oh, there we go. All right, hello everyone, welcome. So today we're going to be talking about conservation of kinetic energy. In previous classes, what we've talked about are what is mechanical energy. So mechanical energy is kinetic energy plus potential energy. So of course, today's focus, we're going to focus on kinetic energy. And kinetic energy is the energy associated with motion. You can find all of this information on the handout that's going around of our previous information. And on the back of that handout, you'll find your predict, explain, observe, explain sheet. And we're going to be using that sheet as an exit slip for today's class. Once we get to the demonstration, I'll further explain how we're going to use it. But just so you know that you do have it as well as this information. So another important formula that we want to remember is our potential energy formula that we talked about last class. This is 1/2. And so kinetic energy is proportional to half of your mass times the square of your velocity. And then we have our 3 types of systems. So a couple of examples we talked about last class. Can anyone give me an example of an isolated system? Now, to refresh your memory, an isolated system is one where you don't exchange any mass or energy. Can anyone think of an example? It's tricky, but...
The universe?
The universe, exactly. That's the only real example that we have of an isolated system. Some people will say that a thermos is an example of an isolated system, but of course a thermos is not perfect. There is some heat that is transferred in and out. A closed system, can anyone, so this is a system that no mass is exchanged, but energy is. Can anyone think of an example of, somewhat of a closed system? Yes?
A greenhouse?
Yeah, a greenhouse, exactly. A perfect example I like to give is the Earth, right? We exchange energy, we get energy from the sun. Now, of course, it's not a perfect system because we receive meteorites and we send out satellites and things like that. So it's not perfect, but exactly. And then an open system is one that exchanges mass as well as energy. Now, can anyone think of an open system that we talked about last class? I think Eve wants to answer this one.
The human body?
The human body, exactly. So we receive energy through the things we eat, and we also get mass from what we eat, and then we dispose of it. But we won't go into how we dispose it. Excellent. So, last summer, August 2014, who remembers when we landed a satellite on a comet? Does everyone remember that? And then that guy was in the news for all that nonsense regarding what his shirt and stuff like that. Yeah, it was a big fiasco. But so we landed we landed a satellite on a comet. How did we exactly do that? So it's not quite as simple as shooting a satellite out to a comet, because this happens. Satellite moves, and then the sun appears. And you can think of the arm as a gravity. It grabs the satellite. So it doesn't let the satellite go out into deep space. There's too much gravity pull from the sun, pulling it back towards itself. So it loses its velocity, loses its kinetic energy. It doesn't operate. Okay? So then, we're going to talk about energy conservation and transformation because we're going to go back and answer that question. How does a satellite actually get out to something like a comet? Or even out to Pluto, right? Things like that. So, energy conservation and transformation, that is our key. Okay? So, when we think of physics, we like to think of in terms of isolated systems where we don't lose energy. Things like air resistance don't exist. Things like friction doesn't exist. It's a perfect world where we can actually observe physical concepts and our math works with it. So, we're going to focus on a closed system because in order for a satellite to get out to a far planet, it needs to gain energy, right? Because as we showed, the sun's just going to keep pulling it back. It needs to gain energy somehow. So we have a demonstration here. We're going to demonstrate conservation of energy. If I can get you, Max, just turn the laptop this way. So the purpose of this demonstration is to show the transfer of kinetic energy. Now on your predict and explain, so on your PEOE sheet, I want you to fill out the first 2 sections, the predict and the explain. So I'll explain what the experiment will be. What I'm going to do is I'm going to lift up these 2 golf balls to about here, and I'm going to release them simultaneously. So they're going to fall and swing like a pendulum back and forth. So, you know, you're going to be writing this down on your worksheets, but what do we think might happen? Can anyone give a prediction of what might happen, let's say, to these two balls? So the ones I release, what do we think might happen with these ones? Can we take any guesses yet?
They'll swing back and forth.
They'll swing back and forth. So, now of course, oh, and I guess that is correct. They will start swinging like a pendulum, and this ball is motionless at the beginning. Do we have any predictions of what might happen to that ball?
Maybe it'll start going up and down.
Maybe it'll start moving. Now, do we have any explanation of why it might start moving based on what we just previously talked about in our concepts of transformation?
Some of the energy from the pendulum swinging balls is being diverted to the string above.
Exactly, that's a very good observation. So, can I get one of you to come up here? Who wants to be the ball dropper? It's a very simple task. Lauren, perfect. So what we'll get you to do is I'll get you to grab the two on the outside, bring them up to about right there. And so when we say you're going to release the balls at the same time, and I want you to notice what happens to this middle ball, but as well I want you to notice what happens to these two outside balls. Okay, so whenever you're ready.
Okay.
And go.
That one starts swinging too.
And then what happens to the ones on the outside?
They swing lower. Whoa.
Wow.
That one's gone higher.
But now what's going to happen?
Then it'll switch back.
And then what's going to happen to the middle one?
It's gonna stop.
It'll slow down, make it slow.
And then what's going to happen then?
And now
It's gonna go
reverse
back
again.
It goes back and forth and back and forth. Now, of course, these are swinging now at different paces. Now, why does something like that happen? Why do our two balls that start at the same time, they're not finishing at the same time anymore, right? And this is due to those external factors, things such as friction, you know, the friction between the string here, or air resistance, right? Things like that. Maybe I didn't tie these just as tight, so this one's maybe more easily able to swing around or something like that, right? So there are discrepancies. So we can do the same thing backwards. If we start with one here, all of a sudden energy is transferred. And then it stops. And then it'll go backwards. So we can think of this whole system here as isolated for our purposes. Why? Because we have things such as friction and air resistance, right? If there was no such thing, these would continue to go back and forth forever because there's nothing slowing them down, right? So it's transferring kinetic energy from one ball into the next. Okay? So what does this mean for our practical terms, using it in space exploration? Okay, so I want to just quickly show this clip. So for those of you that actually don't recall what happened in August 2014, should be opening, we used something called gravitational slingshot or gravitational assistance. Has anyone heard of this before? Can I see any hands? Has anyone heard of gravitational assistance? It's a really cool concept. Interesting.
So it'll go right to YouTube.
Use the Firefox. The Chrome wasn't working.
Chrome wasn't working? Okay. Might not help my time, but this is important to see. Yeah, so what we're gonna show the flight path of that satellite that reached out to the far ends of the solar system. And you're gonna notice something. Since we can't shoot a satellite straight out to a comet, this is what happens. So this does a great job of showing it. So that white line is the path of our satellite. Uses gravity assistance off of Earth to shoot a little farther out. And this is actually what happened, which I think is Extraordinary. Use gravity assistance on Mars. Then again on Earth. And that's the asteroid that we're going to be trying to land on. Do another gravity assist. And each time it gains more and more kinetic energy. Enough that it's finally able to fight the sun's gravity, enough just to get out there. And perfectly intercept
Oh my gosh.
with a comet. So then it does its rendezvous, and then it arrives. So it's an incredible feat for humans to be able to do this. You know, shoot out and land. Oops, where are we? And land on a comet that far away, right? So let's relate the two, right? We're talking about conservation of kinetic energy. So let's talk, for instance, everyone's familiar with the swing of a baseball bat, right? So if we're just going to hold a baseball bat and we throw a ball at the bat, what's going to happen? If we ignore air resistance and things like that, it's going to hit the bat and it's going to come off the bat with the same speed, right? You know, it comes in, hits the bat, flies off, same speed. Same idea works for a planet. Now imagine the planet was not in orbit. It was just moving around. Or no, sorry, just contradicted myself. It's not moving, so imagine it's just standing there in space. The force from the bat is when the ball comes and hits the bat, and then the force shoots it off. You got to imagine for the planet, it's the force of gravity. So if there was no velocity, it would just come around and swoop around, right? Because everything with mass has gravity. So kinetic energy before is the same as after. It didn't gain any speed. So what happens if our bat's moving? So swinging the bat. Okay? Ball comes in with a speed. Ball shoots off with a lot more velocity. It gained kinetic energy from the motion of the bat. Right? Same idea works for a planet. Now this can be tricky to grasp. So the satellite enters the orbit of the planet, just like we saw in that GIF of a satellite doing its 4 gravity assistant maneuvers. It comes in with its speed. As it hits the planet, since the planet has gravitational pull, but it's also moving through space, it steals some of that kinetic energy and it shoots off really fast. Does that concept somewhat make clear? It takes kinetic energy away from the planet and puts it into the satellite. So essentially, it's slowing down the orbit. Every time it gravity assisted through Earth, the Earth loses a little bit of velocity. However, it's such a big mass that transferring that tiny bit of energy from the whole Earth system to the satellite is so minute that it doesn't affect Earth whatsoever, right? You know, recently we took photos of Pluto. Same idea. We used gravity assistance to get all the way up to fight the sun's gravity, right? So the kinetic energy of the ball and the satellite both increase. So the kinetic energy of the bat and the planet decreases, right? So there's a transfer of energy, just like we saw in our golf balls. Transfer of energy from one object to the next. So, what can we take away from this? Energy is never created nor destroyed. Rather, it's conserved, just like we saw in our experiment. It transferred between the 2 golf balls. Now, you notice that these 2 golf balls combined obviously have more weight than the single golf ball, right? So as I'm talking, I'm just going to release this, but you'll notice the center golf ball will actually, it'll swing higher than the other 2 ever went because it has less mass. It gained more velocity, as you can see like it's doing right now. Same idea works with the planet. The smaller mass gained lots of energy compared to the big mass, okay? Google Chrome. So it can be transferred from one object to the next. Universe is, of course, best explained as an isolated system, but things like this, In real world, we think about it as a closed system, same way that we would view a satellite going around a planet. It's taking energy away, but it's not exchanging any mass. It's just a closed system. Forgot to mention this earlier, but hopefully as we watched the experiment, you filled out your observed sections in your PEOE and justified them. I'll be grabbing them at the end of class, and I'll be marking them and answering any misconceptions at the beginning of next class when we have our class discussion. Thank you.